to these concepts in the future, so I thought it'd be good to go over the psychrometric chart. We're just going to talk about the chart today, and then we'll come back later and talk about some of the different parameters on the chart and why they're important to HVAC concepts. So I'm not even going to try to draw a psychrometric chart. The chart looks like this. If you haven't used a psychrometric chart before, it looks like there's a lot going on. Looking at the chart, you see dry bulb temperature, wet bulb temperature, saturation temperature and enthalpy, relative humidity, and several others. The cool thing about a psychrometric chart is that if you just know two of these properties, you can tell a whole lot about the state of the air that you're charting. Let's move this out of the way and then break it down into its components. We'll start with the dry bulb temperature. The dry bulb temperature is the temperature we measure with the standard thermometer. It is the temperature we talk about when we say it's 75 degrees outside. The dry bulb temperature is shown across the bottom of the chart, so let's say 40, 50, 60, 70 degrees and so on, and is represented by vertical lines like this. So let's move this out of the way now. Next we'll talk about the wet bulb temperature. The wet bulb temperature is associated with the water content of the air. The wet bulb temperature is measured with a wet bulb thermometer, which is wrapped in a wet cloth. As the water evaporates from the cloth, there's a cooling effect. This means that the wet bulb temperature is always lower than the dry bulb temperature, except when the humidity is 100%, then the wet bulb temperature equals the dry bulb temperature. On the psychrometric chart, the wet bulb temperatures go diagonally like this. And let's add some temperatures, 90, 80, 70, 60, and so on. Now let's move this out of the way and we'll talk about enthalpy. Enthalpy is the measure of heat energy in the air due to sensible and latent heat. Think of sensible heat as the temperature of the air and latent heat as the moisture in the air. The enthalpy is shown above the saturation temperatures. It's in units of BTU per pound, and it runs diagonally like this. Let's move this out of the way and talk about relative humidity. Relative humidity is the amount of water air can hold at a certain temperature. Warm air can hold more water than cold air. The humidity lines are curved like this. So this would be 10% relative humidity, 20%, 30%, and so on. Zero humidity is the dry bulb scale down at the bottom, and 100% humidity is up at the saturation line here. Relative humidity is a percentage, so 70% relative humidity means that the air contains 70% of the water it can hold at that temperature. So let's move this out of the way and talk about absolute humidity. Absolute humidity, also known as the humidity ratio, is the vapor content of air in pounds of water vapor per pounds of dry air, or on my chart it'll be shown as grains of water vapor per pounds of dry air, where 7,000 grains is 1 pound. It is shown on the right side of the chart and goes horizontal like this. Think of it like this. If it's cold outside, you could have 90% relative humidity, but the actual amount of water in the air, the absolute humidity, is still low compared to if it's 70 degrees outside and 90% relative humidity, or even 50% relative humidity. Let's move this one out of the way and talk about the dew point. The dew point temperature is the temperature at which water will begin to condense out of moist air. It's represented on the 100% humidity line, and it's read horizontally on the psychrometric chart like this. Now let's move this out of the way and get to specific volume. The specific volume of air is the volume that a certain weight of air occupies under specific conditions. Specific volume is shown with diagonal lines like this. The units are cubic feet per pound of dry air, so it's 12.5 cubic feet per pound, 13, 13.5, 14, 14.5, and 15, like that. So let's move this out of the way one more time and talk about vapor pressure. Vapor pressure relates to the number of water vapor molecules per cubic meter, and it's linearly related to absolute humidity. Vapor pressure affects the evaporation rate. When the humidity is high, the vapor pressure is high, and this is why there's very little evaporation in humid climates. It's shown on the right side and goes horizontally like this. It's in inches of mercury, so 0.2, 0.3, 0.4 inches of mercury, and so on. So let's move this out of the way and bring back our psychrometric chart and do an example. Let's say you have a space at sea level that is 70 degrees and 50% relative humidity. Let's find the other properties in that space. So let's put a point on our chart at 70 degrees and 50% humidity. Now going over to the wet bulb temperature scale gives us a wet bulb temperature of about 59 degrees. Drawing a line over to absolute humidity gives us about 56 grains per pound. And if you continue over, you get about 0.38 inches of mercury for the vapor pressure. Drawing a line to the enthalpy scale gives us about 26 BTU per pound. And you can see that the specific volume is about 13.5 cubic feet per pound. Drawing a horizontal line to the saturation temperature gives us the dew point of about 50 degrees. So look at how much information we got just by knowing the temperature and relative humidity.